And then, you know, and then the more at some point.
Because I can record it, but if you want to share the screen, I'll be recording this.
J'ai comme l'impression d'avoir vu félicitations. T'as connu 2 voyages, 2 semaines de suite.
Oui, mais le deuxième, je ne savais pas avant d'être revenu d'Ottawa.
OK.
C'était comme vraiment d'énervé.
Ah, c'est vrai. Je savais que c'était à peu près dans cette période-là, mais il y avait pas de.
Oui, mais je savais que la réponse allait être. Puis là, que dans la fin de la semaine dernière, ils m'ont demandé les étudiants
Et comme c'était. J'ai oublié de te demander c'est là, ça vaudrait sûrement la peine de le dire. Non, mais non.
Oh. I can do the microphone here. Okay.
Double like.
So I want to, what did I do? I said hide floating meeting controls.
Yeah, but I think it's right there. We can just, oh yeah.
I unmuted myself.
Oh, yeah.
Is that okay?
Perfect. Yes.
But yes. And I put the talking box down here and hide meeting controls.
Learning Zoom on the spot.
Right, and then we go here.
Perfect.
And then we go here. And we then hopefully. That's up like that. Yeah.
Yes. And unfortunately, this is like a problem we've been trying to solve now. This can be shut down.
Oh, yeah,
It's a
fine.
bit annoying.
Oh, wait,
Yeah.
Bonjour tout le monde, merci beaucoup d'être venu ici aujourd'hui. C'est un grand honneur que je vais introduire notre conférencière aujourd'hui, Rugheimer. Je vais donner sa présentation en anglais si c'est vrai. So Dr. Sarah Rugheimer is an astrophysicist and the Alan Carswell Chair at York University in Toronto. She works on how to detect life on an exoplanet by looking at atmospheric biosignatures. Her research interests are modeling the atmosphere and the climate of extrasolar planets, with a particular focus on atmospheric biosignatures in Earth-like planets, as well as modeling early Earth conditions. She earned her bachelor degree in physics at the University of Calgary, and then moved on to do a master's degree and PhD at Harvard in astrophysics. She then took a Simon's Origin of Life Research Fellowship at St. Andrews University, followed by a Gladstone Research Fellowship at Oxford. On top of that, she is also interested in public outreach. Her TED Talk, The Search for Microscopic Aliens, has more than 1.7 million views on YouTube today, on TED.com. And she has previously been awarded the Barry Jones Award and the BSA Rosalind Franklin Lectureship in 2019, and a Caroline Herschel Lectureship Prize in 2018. Her new astrobiology course for the public is available online on Amazon Audible Originals, called Searching for Extraterrestrial Life. So without further ado, let's take the stage.
Thank you so much. And thank you for being here today. This is by far the largest colloquium seminar I've given are we in the post-COVID era? I'm not sure, but it's really great that everyone's here, and it's nice to see so many faces that I remember and new faces as well. So I'm going to be talking today about biosignatures through rocky planet evolution around different stellar types. And I wanted to start with just contextualizing this, since there's this bridge, right, with exoplanets and our own solar system knowledge. And the one thing that we can do with the solar system is we can know so much. You know, people care about slight deviations in the ozone profile on Earth, and that is really important. We cannot know that much about exoplanets, right? We can know exoplanets, maybe their mass and their radius within 20%, and that's like a really great characterization right now. And so we really have a trouble with when we're trying to figure out these linkages. However, with exoplanets, we can know about so many different exoplanets, and we can start to get a statistical understanding of planets that we cannot get from our own solar system. And so this is where I feel like there's a great bridge that can happen between the two communities. So I call this the timeline of excitement. We've had so many missions over the past few decades and coming up that have found exoplanets, that are characterizing exoplanets. Of course, we have entered the James Webb Space Telescope era. We've had our first observations of the atmosphere of exoplanets. And, you know, it's going to be harder, but we will hopefully be able to do this for a few small planets with James Webb. The error bars will be a bit much, but we'll be able to do it. And I think that's really exciting. On the other hand, James Webb is mainly going to be doing gaseous, Neptune-sized planets. It's going to be able to do a few super Earths, a few Earth-like planets, but we're really talking just a handful of Earth-like planets, maybe 6, maybe 10, not that many for James Webb. And so what I am then wanting to see happen is we'll have the Plato and Ariel era. We'll have Plato, which will determine accurate densities, compositions, Ariel, which will be able to be the first dedicated mission to look at thousands of planets to detect atmospheres. Still, they're not getting to those Earth-like rocky habitable planets, though, that I'm interested in. So I want to see signs of life before I die. That's the only reason why I got into astronomy, quite frankly. So what do we need? Then we need something like LUVOIR, LUVEX, or HAVEX, or whatever mission, like that. Hopefully it flies, and also maybe something like LIFE, which would be in the infrared. And this is a mission that I'm on the team for, because I think there's just more fun things in the infrared to observe than in the visible. But both of these together will do a great job of actually being able to characterize these planets. And so, fundamentally, the reason why I got into astronomy is this question: are we alone in the universe? And I think when I started graduate school, I thought we would have a very clear answer. And now that I'm here, I don't think we're going to have a very clear answer as we go forward, but this is what this talk will be about. So I think the public expects, when I talk about finding life on another planet, this is what I'm referring to. We're going to have, an idea of continents and vegetation and life, that's complex, and tall people with blue tails. What I, as a theorist, claim we're going to find is this beautiful spectra. No noise, something with clear, easy to see signals. Maybe you'll have signs of vegetation, methane, oxygen, ozone, water, carbon dioxide. And of course, what we're going to find is there's going to be a fuzzy pale blue pixel. It's going to be difficult. There's going to be a lot of error in our measurements. Multiple models might fit the measurements at the beginning until we figure out how to break degeneracies, and there's probably some degeneracies that we just can't break. So that's, when I think of it, I think there's two main challenges. There's a technological hurdle of just being able to do the detection. If we want to be able to detect oxygen, say in an exoplanet atmosphere, that is a huge accomplishment. And hopefully we are nearing that, and James Webb should be able to maybe detect ozone. That's exciting. But that tells you nothing about whether that's life or not, really, because then we have the second hurdle, which is the interpretation hurdle. Did that actually come from life? Is that some other geological process? What are these planets doing? How well are we going to be able to find the context of those planets? So I am speaking about future observations here, though James Webb is reducing that timeline. But here we can see, we have Earth, Venus, and Mars, and their IR spectrum is very different, and we're hoping to then get lots of planets spectra and to start to see patterns, to see these differences, and to see what we can learn from them. So when we think about the technological hurdles, we have the space-based telescopes, James Webb, Ariel, and then we have large ground-based telescopes like the ELT with METIS being the prime example. And there's really trade-offs between these two types of missions. So with space-based telescopes, they're lower resolution, but because you're able to get the line profile, you're able to measure or have a more accurate understanding of abundances of molecules, which is great because that gives you a lot of context about how important is this molecule. And from the ground, you can't do that, but you can use high resolution spectra, and that will allow you to detect the presence, but it'll allow you to detect even minor molecules, even isotopes in an exoplanet atmosphere. So we're able to detect much more minor things rather than big gases, but not the abundance. So there's really trade-offs between these two types of observations. Oops. No, come back. Okay, so as I said, we have this first opportunity that's happening now with James Webb, and then we'll have more data with Ariel. We're having ELT with METIS coming online, hopefully in the mid-2020s. And then there's this 25-year horizon, hopefully, fingers crossed, where we're going to get even bigger telescopes in our lifetime, which will be able to characterize the atmospheres of smaller rocky planets. I just like thinking about this also when we think about the technological improvements of Pluto, like what we thought Pluto looked like. This was the image we had of Pluto in 1930. It's about like our exoplanet, like direct detection exoplanet of a hot Jupiter, or something like that. I'm not hot Jupiter, but like a newly formed Jupiter right now. So that was 1930. Then you have Pluto with the Hubble Space Telescope in 1994. And then after they did some upgrades to Hubble in 2003. And so that's quite a big jump, in our resolution just in, a bit over 70 years. This is a little unfair because this is a flyby, but we can see snow-capped mountains on Pluto now, which is great, and so we're just seeing these massive technological improvements. Same with I love the images of Jupiter with the Juno spacecraft. They're just so beautiful, and we're able to learn a lot about atmospheric dynamics with this higher resolution data, and even detect clouds on Jupiter. I mean, it's amazing. It's amazing. So yeah, so then we have these technological hurdles, which hopefully we're going to step by step get more telescopes to be able to do that. But then we're still left with this interpretation hurdle. And Thomas Kuhn, who wrote this book on scientific paradigms, he says what a man sees depends, or woman depends on both what he looks at and also what his previous visual conceptual experience has taught him to see. Now, this is really important, I think, when we think about, say, phosphine on Venus or other things. Are we seeing what we want to see, or are we seeing the data as it actually is? This is a simple example, but all of these balls are the same color. It's just an optical illusion, right? But your eye is expecting something, and it's not able to parse the real color of what's happening. because of our expectations. You can't even see, you probably wouldn't even bother to think of like, are these the same color balls if you just saw this and you didn't realize what you were looking at, you just move on. You'd be like, oh, there's a bunch of different colors here.
If we had a spectrum of these balls.
Yeah, what you can do is on your computer, you can go and find like those little RGB color pickers and you can prove with yourself they are indeed the same color. And this is not that I'm not like messing with you, which is what I did, you know, because it's like I cannot see them as the same color ball, even if I like, anyway. Yeah, so it just to say, like, our own kind of interpretation of what we think we might see or what we want to see really strongly influences us in data, and we see this in science all the time. You know, again, a quote from Feynman: "Science is a way of not trying to fool yourself. But first principle, you must not fool yourself, and you are the easiest person to fool," right? So this is an example of the Viking. Remember this Cydonia region on Mars? Have you guys come across this face on Mars? Because humans see faces really easily, and with low resolution data, it's like, oh man, there's a face. Maybe there's a civilization there. Maybe it's a beacon, you know, a message. And with higher resolution data, it just goes away, you know. And so a lot of the controversies I think that we find in exoplanets, in astrobiology, say Oumuamua, they're just low resolution data problems, right? Like we're like seeing what we want to see with low resolution data. That's like my interpretation of it. At least, at the very least, I think we need to be careful, because with low resolution data, we can overinterpret very easily what we're seeing. So this pale blue pixel problem, the image is going to be very difficult to interpret. There's really only one type of detection that would be unambiguous of life. And that is, of course, this like, hello, you know, Earthling signal. Then we would know we found life. Everything else is going to be really difficult. So this is where I spend most of my time. And really the three areas that I'm interested in are stars, how they influence planet atmospheres, and then how microbes influence the atmosphere and how those all play together. And in particular, I'm interested in the UV radiation and how those link together. So there's two ways of searching for alien life. You know, we can look for life as we know it. I'll talk a little bit about why the pros and cons to these. And one easy example to think about is looking at Earth's spectrum. You know, would an alien looking at Earth, would they be able to tell that we have life on it, on this planet? And you have the sun spectrum, here's visible part of Earth spectrum, the infrared part of Earth spectrum, and you see lots of molecules here that could indicate that we have life, in particular, the combination of oxygen or ozone with methane. You have a signal problem, you know, it's 10 billion photons for every photon in reflected light for an Earth-like planet, or a million in the infrared. Then there's looking for life as we don't know. This is trying to be a little more agnostic, considering all the different types of molecules and would they exist on their own without life. And so it's a question that I always get, so I think it's worth talking about and how to frame this. Like, we could look for alternative biosignatures. And I mean, indeed, probably we should, right? It's not Earth-centric. The cons is we have no idea like what those are. That's the problem, right? Is with an alternative biochemistry at this point, we don't have enough advances in synthetic biology on Earth. We don't have enough solar system exploration of weird environments, say like Titan, to really be able to see whether these types of biosignatures, what would be a biosignature in an environment. Take Titan, what's the biosignature there? Should Titan life exist? You know, it's, you know, I mean, if you can tell me, then we can look for it. But it's like, this is the problem. It's interesting. And I think we should, you know, first look at our own solar system, because we can't tell if there's life in our own backyard yet, you know, on Titan, Mars, Europa. So this is where I think we should do a lot of solar system exploration in weird environments on Venus, on Titan, you know, as well as more classically Earth-like habitable environments like Europa. Europa's been classically habitable in an Earth context for 4 billion years, you know, might as well look there. And Enceladus, you know, Mars. But we're still, you know, going to have to look probably with this understanding of we need more data in order to do that for exoplanets. Then we could look for unique biosignatures. Now, these are things that are only produced by life on Earth. So there's no known false positives, which is really great, right? Because then you see them in exoplanet atmosphere. They're not really produced by geology and physics. Awesome. The problem is they're very rare and usually limited to a single microbial species. It's an evolutionary quirk. It's not a main metabolic pathway. Oxygen, methane, those are main metabolic pathways, right? Which is why they're so much more abundant in the atmosphere. So they're only produced in very small quantities. And furthermore, we don't even have the spectra for most of these molecules, which is a real problem. Because of the 16,000 possible molecules, we only have spectra for 0.04% of those molecules. So we couldn't even identify them in an exoplanet without having the spectra of those first, So then it's kind of going back to searching for Earth-like life, or at least carbon biochemistry-based life. What I would say there is water and CO2 are abundant in the universe, the main things that life uses on this planet. Carbon is more abundant than silicon. It forms more complex chemistry. Water is polar, has unusual properties, remains a liquid over a wider temperature and pressure range. There's reasons to first look here when there's so many billions of planets that would be expected to have classically habitable conditions. So the pros is we might understand what we see. Oxygenic photosynthesis, I get this question a lot, and so I want to try to give this nugget to you because you might come across it when you're talking over some beers about it. Why do we go after oxygen? This is a common question. So oxygenic photosynthesis is a more advanced metabolism. It takes two photosystems, so it evolved a little later in life than methanogens, but it uses light, CO2, and water, the most abundant things, for energy. Most other redox pathways are confined to smaller niches, are limited by a certain molecule, but CO2, water, and light abundant. And so once evolution, was able to use these three things, it became the most dominant biomass building product on our planet. And so that's why, basically, because then you get oxygen from those things, and these are abundant in the universe. There's no and also as a side note, all complex life then uses oxygen, but that's not why oxygen's in our atmosphere, right? So oxygen respiration gives you the most energy gradient in a redox pathway. So all complex life uses oxygen because you have the highest metabolic energy gradient, but that's respiration. That's different than oxygenic photosynthesis. That's another thing that I think people get confused on. Okay, so there's no shortage of places to live, 40 billion or so Earth-like planets in our Milky Way. The cons are all classical biosignatures, especially of single gases, have known geological and photochemical false positives because life is using the same pathways that chemistry and geology uses. So you need multiple gas detection, maybe even multiple telescopes like a LUVOIR and a LIFE mission flying together. It becomes a lot more expensive. And still we might be fooled. We can't go and visit these planets. We don't have warp drive yet, and maybe ever. So the false positives are also strongest for M dwarfs. The UV environment is vital, and we need to understand the star. So, we only will understand the planet as well as we know the star, and stars are difficult, and planets will vary a lot in their compositions. So these are kind of the problems that I got interested in. When we think about what happens in an atmosphere and how it relates to exoplanets, so we have incoming star radiation. You have some absorbed by the surface, some is reflected by the surface, some is reflected by clouds. That would be your visible part of the spectrum. Then you have what's absorbed by the surface can get re-radiated out as radiation, and that will escape to space. Some of it gets trapped in greenhouse, and then that's the infrared part of the spectrum. So the models that I use are three broad models. One is a climate code it assumes a fixed chemistry, and then it calculates the temperature and pressure in water. And then the photochemistry with the fixed temperature pressure updates and calculates with the UV light coming in what the gas composition is. And then those two models can go back and forth until you have a stable solution of your atmosphere. Then you can put the output. So this is the atmosphere model. So what is in the atmosphere? Is it physically plausible? Because retrievals don't necessarily care about whether something's physically plausible. So you kind of need to do both forward modeling and retrievals, when you're thinking about exoplanets, because you want to physically motivate what you're seeing, And then if you output the atmosphere, you can predict what spectra would look like, see if your instrument could detect it, run retrievals, and see if you're actually going to be able to measure this with a telescope. So that's kind of the three models that we go for. And what I'm interested in is like what wavelengths, what resolution, how big of a telescope do you need, to be able to do these things. And particularly, I look at mostly how does the star influence all these things and the UV radiation. So as you are, I think all astronomers, are there planetary scientists here as well? Is it astronomy? Some planets? I see a planet. Okay. So for the non-astronomers here, because we name things really odd that are difficult to follow. So we have FGKM stars. The sun is a G star, and most stars are actually smaller, the K and M stars. And broadly speaking, F stars are bigger, G stars are like the sun, K and M stars are smaller. You're going from higher UV environments to lower UV environments. And UV destroys some biosignatures like methane, making it harder to see in the atmosphere. But it produces other biosignatures like ozone. Ozone is much easier to detect than oxygen, and you get ozone only from UV light. So what we think about, though, is it's not just the total amount of UV, it's this ratio of how much is in the far UV and near UV part of the spectrum that also matters. And this is because different reactions will proceed only by some wavelengths of light and not others. So the reactions that produce ozone need far UV light, but the reactions that destroy ozone can proceed by near UV light. So it's this balance of how much UV and in what kind of areas you have UV that really matters. And so then when we go back to, I made this claim that, hotter stars have more UV. And that's true because they have a lot more near UV because their black body is still in the UV part of the spectrum. So they have tons of near UV, but they have a relatively small amount of far UV. And then you get to M stars and they have almost no near UV because their black body is so shifted to redder wavelengths, but they have a lot of far UV. So that really changes then the types of reactions that happen in planetary atmospheres. So this is especially important for M stars, where I'm going to spend a bit of time talking. And M stars are really interesting because if we look at all of the stars within 10 parsecs or 32 light years from the sun, we have 20 or so stars that are like our sun. And then, 75% of them are these M stars. They're so much smaller. And so that's our first targets of interest. Those planets will be where we'll look first. And that's exciting because Kepler showed us that about 1 in 4 M stars have a habitable planet. And you have some advantages, especially in transmission spectroscopy, because the amount of light that a Earth-like planet around an M star blocks out is much more than the amount of light that a Earth would block out over a sun-like star. So you have a bigger feature depth. Also, the habitable zone, which is, I'm interested in these rocky temperate planets, it's much closer in for M stars. And so the planets are going to be transiting more frequently. So that's exciting. The problem is M stars have big flares. They're kind of buggers that way. It's a real problem, because we don't yet know a lot about M star UV activity, and we're still trying to figure that out. And hotter M stars are active for a really long time. So, all M stars are active for a really long time. But hotter M stars are active for 1 to 2 billion years. And then these cooler M stars are active for 6 to 8 billion years. That's longer than Earth has been around, right? So they're just active for huge amounts of time with huge flares going off, sometimes daily flares and then a big flare like every 200 days. Do M star planets even have atmospheres? It's like the #1 question that I want JWST to answer. And when I say atmospheres, I mean thin atmospheres. So nothing like, we know that planets around M stars can maintain a much thicker atmosphere, but can they maintain a 1 bar atmosphere? And that's what we mean by thin atmosphere. We don't know. It could be that the flares just strip off the atmosphere and then you have a bunch of rock balls, and then you've answered, why are we not around an M star? So I'm really curious about that question, actually. So modeling with the real UV is really important. For a long time, this wasn't really done. So this is the Phoenix model. These are the model of an M star. And then this is the UV data, right? So the models do really great not in the UV, and then they do really poorly in the UV. So you have, this is the photosphere, this is non-UV radiation. You have this near UV. Remember how I was saying for M stars, the more cooler ones, their black body is following this curve, and then their UV is different, right? So you see that. And then you have the far UV here. And if you were to naively just take, though, a stellar model that you can pull online from the Phoenix models, and you were to use that for your photochemistry input, you would get very bad results because, you know, there's like 10 orders of magnitude difference here. And this black line is a flaring early young M star, and this green line is a typically quiescent M star with a muscle survey that is still quite UV active. So yeah, so when we think about active stars, we have better characterization of active stars because the UV is has enough flux for us to measure. But these inactive stars get really difficult because we know some of the emission lines, but we don't really know where the continuum falls, if that makes sense. So like, is the continuum down here? Is it down there? We don't really know that yet. And that's something that hopefully we will still manage to get with Hubble while we still have a UV mission in space. Because this actually kind of matters, like in your modeling, how much UV is in the continuum versus in the emission lines for these cooler M stars. And as I said, they're going to be the first planets we detect. So, you know, that's something I'm very interested in having happen. So when we think about M stars, you know, this is the flux of M stars. This is a hotter M star or a cooler M star. You know, like, of course, most of the flux is not happening in the UV. This is the UV part of the spectrum, but it dominates the photochemistry. This is like where all the action is happening on your atmosphere. And so to show this, I just want to compare two extremes of like the same exact planet with the same fluxes going into the atmosphere, orbiting an M5 star, middle of the temperature range, with a UV active versus no UV, you know, just like a theoretical minimum probably doesn't exist star. But it just shows you how much that little part of the spectrum really matters, because that's the difference in the spectra. It's like completely different, you know. So the amount of UV that we model for atmospheres really will change what we expect. So we will need to know also the UV of a host star in order to be able to understand what's happening in the planetary atmosphere and to contextualize our predictions correct. So when we think about the known false positives for oxygen and ozone, here's a smattering of them. Most of them are prevalent for M dwarfs, and all of them depend on the UV radiation. So you don't have false positives for oxygen and ozone without UV. So again, this is why it's really important to understand the UV of the star and what's happening. For example, you have extreme UV breaking apart water into hydrogen and oxygen. The hydrogen is light and it escapes. You're left behind with oxygen, you know, in the atmosphere, and the planet might be dry and has lost all its water permanently. So, you know, one way to say mitigate against some of the false positives to look for water. If you don't see water, then that's probably a false positive scenario. You know, but there's other scenarios where you could still see water. Anyway, so that's just like an example of how you might get a false positive. So on Earth, for life to as biosignatures, these are the strongest biosignatures, and it's not really either or, it's both of them together. So you have oxygen and ozone from plants, from microbes, you know, about 50% comes from microbes, 50% comes from plants and trees and grass and whatnot. And then you have methane, which is produced in, I can't remember, it was like 100 times more or so than it would be through just volcanoes. But, you know, you could produce oxygen with UV light by breaking apart water of CO2, and you can produce methane by volcanoes. And depending on the redox state of your crust and your planet, maybe those gases accumulate in the atmosphere, right? Because it depends on them how much they're going to react with the surface to see like what's happening. So either of them alone are not a good biosignature. So on Earth, we have oxygen, methane being produced by biology, but if biology were to just be wiped out tomorrow, these gases would react in the atmosphere and they would no longer be simultaneously present, which is why it's the combination of both of these gases which indicate life. And so that's still the strongest biosignature to date. It was one of the first biosignatures that was thought of. And sadly, it is still like our main biosignature that has not yet been like toppled, you know, because oxygen alone has been toppled, you know, methane alone. So, you know, if an astronomer alien, if she was looking at Earth, they would see oxygen and methane, right? And that's how they might figure out that. All right, so I hope I've convinced you that the UV matters for stars and planets. And, you know, so I want to think about, okay, well, let's look at oxygen and biosignatures through geological time on Earth, because Earth has not been one planet. It is an exoplanet in some ways. It's been like thousands of planets, and it's biogeochemical lifetime, right? So, you know, we've had the Hadean era, we've had Archean era, snowball, Triassic period, like so many types of atmospheres that have existed on Earth. And so we can think about, you know, if we think about history of life in 1 hour, you know, we have the formation of the planet about 0 minutes into the hour. The origin of life, you know, people debate this, but, you know, 3.9 to 4.4 billion years ago, 9 minutes into the hour, depends on when the Earth cooled and was happy and stable. The oldest signs of life certainly are around 3.5, definitely. Some people argue 3.8. I've even heard 4.1 argued as isotopic evidence of life. So, you know, we have definitely, though, 14 minutes into the hour life. Oxygenic photosynthesis, that's that system I told you about using UV light, CO2, water. That was at least in play by 2.7, and there's probably a lot earlier. It's hard to detect because we don't have good estimates on that. Then it took a really long time, though, you know, to get multicellular life. It's about 1 billion years ago, so 47 minutes into the hour. So almost all of Earth life history has been dominated by microbes. You have land plants, you know, 500 million years ago, and then anatomically modern humans that, you know, are exactly like us about 300,000 years ago, or the last second of this hour. So most of this time has been microbes, you know, and even, I don't know if you guys have heard of this, but it's half the cells in your body are microbial cells and half are human cells. You know, are you human? Are you microbe? I don't know, you know. So yeah, so we have here, you know, Earth's atmosphere. Also, there's a lot of the air bars get really high, you know, in the early Earth atmosphere because it's difficult to know. We don't have a TARDIS, but I wish time machine to get there. But anyway, so you have oxygen certainly below this amount, and then it's like risen in these steps, you know, and so and then you have methane coming down, CO2 broadly was coming down, and too, like, people debate what was happening with nitrogen a lot. But yeah, so you can think about, you know, say maybe let's take 4 time points, you know, of a prebiotic planet. After the first rise of oxygen, then there was a second rise of oxygen in modern Earth. We can put those around different stars to see what's happening. So basically taking these different planets, putting them around hotter F stars, around sun-like stars, and then the cool M and K dwarfs. And that's what I'm going to be showing you next in this figure. So on this top row here, we have the prebiotic model for all these different star types. So the F stars are the black line and purple line. And then as you go towards the red, that's going to cooler star types, right? So that's your prebiotic planet. Then you have the first rise of oxygen with 1% PAL. We already have ozone starting to pop out, but only for the F stars, you know. Then after the second rise of oxygen, O2, again, we have more oxygen coming out. This methane feature was, of course, strongest here. It's starting to diminish a little bit. And then modern Earth, you have ozone appearing for all stellar types, but a less strong methane feature. So ideally, you know, you want to think about this ozone feature, of course, because it comes out very early, especially for hotter star types. It also, unfortunately, overlaps with one of the CO2 features if you have a lot more CO2 in your atmosphere. So then you'd really have to try to tease out, like from the wings of the CO2 line, whether you also have ozone. That I think that could be difficult. So, you know, in Earth's atmosphere, we had, this was modeling with like 10%, like a 0.1 bar of CO2, and then it went down more quickly. And so then you don't have that double feature. But you could easily imagine a scenario where you have, you know, a 10, like a 0.1 bar CO2 in your atmosphere, and also oxygen and methane, right? Like that's not too hard to imagine. You know, so anyway, that could be a problem. you want to ideally detect something like methane and ozone together, and in the IR, that's the easiest way to do that. Of course, we have high uncertainties in the absolute abundances, like I said, back in Earth's time. So one project that I did with a student in St. Andrews is we looked at, can we use modeling tools from astronomy to help geoscience, and figure out, can we find constraints on the O2 abundance in history? And so this is, oxygen levels that are basically where they're not compatible with geological proxies, where they are compatible with some proxies, and then, fully compatible. So this is, we get a tighter constraint since we come to earlier history. And most of modeling has done kind of like, we just fix like the oxygen amount, and then we have our model tell us what the flux is, because you can do it that way. You can say, we definitely have, 21% oxygen, what flux gives you that? That's how all modeling had been done up until my student worked on this. But that's not really biologically reasonable, right? You would expect biology to produce some oxygen, produce a little bit more oxygen, a little bit more oxygen. So you would expect it to go up like flux-wise, in that way. And what she found is when you do that, that just goes away. Like that's a region of instability. So through like ozone shielding and whatnot, you have like a bistable state of when you increase oxygen. And so that's really interesting, right? So you have this, like, depending on the amount of methane you have around, because of course that'll take down some of your oxygen. So in any kind of ratio of methane to oxygen, you'll get different amounts of oxygen and ozone, but you still have this unstable region in the middle, which I think is really, really cool. And so that probably means that we can then constrain Earth's earlier history of oxygen by doing this atmospheric astronomy modeling. So here's a much more complicated plot with all the different types of isotope and geological evidences for different life. And basically then we can start to constrain it earlier a little bit more with the modeling, that it indicates oxygen was below a certain amount. And then once there's enough flux building up, it kind of flips up to a higher oxygenated state. So that's that. We can also do things like, well, what about the Archean pressure of the atmosphere? Because again, how do you know the pressure of the early atmosphere? It's very difficult. So you can help constrain the pressure by using atmospheric modeling. And so one of the projects I did with Paul Rimmer and Ollie Shortall at Cambridge, they looked at oxidation of micrometeorites. And then we modeled those constraints on, well, how much oxygen do you need to oxidize your micrometeorites? And then that tells you something about the atmospheric pressure and indicates that the atmospheric pressure in early Earth's history was around 0.3 bars, so much less than current oxygen levels. And that also matches with like some raindrop data and some other interesting effects. Wouldn't be an astronomy talk about exoplanets if I didn't mention clouds, because clouds are going to be a problem. So clouds, let's look at clouds on the oxygen band. So they do some interesting thing, right? Because, it does clouds as you, so let me try to orient you here. So we have, this is our current oxygen levels, a 10th and a 100th of oxygen levels. Those are those two rises of oxygen I mentioned. And when we go from 0% clouds up to 100% clouds. And so you can see the feature is slightly declining, not as much as you might think, because oxygen is really well mixed in the atmosphere. So there's a lot of oxygen above those cloud layers, which is great. But it does decrease the feature depth. But what's also interesting, though, is because clouds have this higher albedo in the visible, they actually make it easier to see in many ways, because you have a higher albedo, so you get more signal. Even as you decrease the depth, you get a lot more signal, and because oxygen goes fairly high up in the atmosphere, you actually see that. So then we worked with another student at the Kavli Summer Exoplanet program, and she looked at how we could detect O2 with LUVOIR and at different epochs in Earth history. And so you see, like with it at 100th of our levels, it's really difficult. Probably beyond the number of hours that a telescope committee would want to give us. But then you start getting like to a 10th and modern levels, it's very easy to detect for most cloud coverage and cloud altitude. So this is cloud coverage and cloud altitude and hours, so like 10 hours, of detecting oxygen. So that's really exciting, but like not very good for that. What was really depressing about this study though, is because LUVOIR would like to also detect methane. That would be great, but it's just not detectable for Earth-like concentrations of methane. So getting that high amount of oxygen and methane together is just not like really in LUVOIR's range. It might be like at where you have lower amounts of oxygen and higher amounts of methane. LUVOIR could still do it. That would be this thing. But at like a modern Earth case, it's like tens of thousands of hours. It's just like not. And that was like when we were assuming not like a 12 meter, 16 meter like telescope, let alone like the 6 meter one that was mine. So, this is just not going to happen. Well, but water will be really easy to detect, so this is water. It's like, I don't know, an hour or something. But then it's really hard if you had a totally opaque cloud deck at high altitude, because there's less water in the stratosphere and most of the water is in the troposphere, then you won't be able to detect water. So that's what that's showing. That's why there's those very higher observational times. So the last thing I wanted to talk about in this talk is like, well, what about prebiotic signatures? Like not just, oh, the signal cut out. Are we back? We're back. What about prebiotic signatures? Because I want to find whether there's life, but you also might want to find, is there a failed biosphere or a stalled biosphere or biosphere on its way? If you're looking at a really young system, and I love this quote by George Whitesides, it's a long way to go from slime to Mozart. It's very poetic, but Steve Benner, prebiotic chemist, said, well, it's a long way to go from HCN to slime, right? Like we actually kind of know how you go from single cell life to complex life. That's fairly well understood. We don't really know how you go from a molecule to life. There's a lot of interesting research that's been happening in origins of life chemistry, but this is really where the interesting origins research is happening. So we can look at these different prebiotic signatures because we know what molecules life seems to use on Earth for DNA and RNA and proteins and whatnot. And then you can see like, well, where are these absorbing and what things produce it, whether it's lightning impacts and whatnot for that. So we looked at, for example, just changing the carbon to oxygen ratio in your planetary system and what types of prebiotic molecules would be there. So this is a very Earth-like environment. And basically, as you increase the carbon to oxygen ratio, you get a lot more nitrogen and rich species, more reducing environment, and have like more amounts of these prebiotic signatures. And so the HCN we focus on because this is a very important prebiotic molecule that seems to be needed by a lot of things. Will depend on the C to O ratio, and in particular how much methane that there is, and then what the ratio of how carbon is being, what's the word, taken up by the how the oxygen is bonding and where the hydrogen is will depend on the redox state of that planet. So here, this is just basically showing that depending on the C to O ratio, it's more tightly constrained hydrogen cyanide mixing ratios for the lower amounts of C to O and the higher amounts, but in this mid-range, depending on where the ratio of C, carbon monoxide, carbon dioxide, and methane goes, you'll change the amount of hydrogen cyanide you might expect. So we wanted to see also then specifically, my interest, how much does the UV influence the amount of hydrogen cyanide in the atmosphere? And so you can see here, if you have flares, you get a lot more hydrogen cyanide. That's this red part, much more hydrogen cyanide. But if you have atmospheric absorption, or like clouds or haze or something blocking the atmosphere, then you have a lot less hydrogen cyanide appearing. And so this is a kind of a spaghetti plot, as they call them. So basically, this is just showing you the range of mixing ratios of abundances of hydrogen cyanide you might expect. So you can see it spans several orders of magnitude, depending on how much hydrogen you have, how much methane you have, and then of course also the UV. So I wanted to see could you detect this for the early sun or an M dwarf? And so just show you the spectra for these types of environments. Now this is with like very low amounts of hydrogen and low amounts of methane. And these blue gases are your main atmospheric absorbers: water, methane, CO2. You don't really need to pay attention to them, but those are just the dominant contributors to the spectrum. So you can see that with those three, then you get the black line, which is the spectrum. Then you start to, you know, increase some hydrogen. You start to have a little bit of HCN coming out. And then when you have higher amounts of methane, definitely lots of hydrogen cyanide coming out, as well as some ethane. And with high amounts of both, but you get the strongest features. Sadly, because these are all in the wings or lines of other features, they just don't influence the low resolution spectra. It's like, you know, it looks so promising, but then you can't actually see really the difference in low resolution between these black lines, right? Like they're basically the same black line throughout for these different you know, models. So then, okay, well, what about high resolution spectroscopy? Like I mentioned, right? So you can have this situation where the planet is going around the star and you can actually detect lines like carbon monoxide, for example, by the Doppler shift of the planet going around its star. It's very, very cool spectrum technique. You can use cross correlation with high resolution, you know, where you just march across your template spectrum and you get a match of a molecule, and then you've detected that molecule in high resolution. You can go through Earth's atmosphere because the motion of the planet is making that line drift across the spectrograph, so you can see through Earth's own molecules, its own carbon monoxide and stuff. It's a very, very cool technique. And so we've already detected HCN in a hot Jupiter. That's this, that's like a transit, you know, so it's that like angled line, super cool. And what blew my mind is we can actually do isotope planet, what? You know, yeah, so you can have carbon monoxide with C13O and C12O. Those high resolution spectra are very different, right? And so Paul Mollier looked at this, and this was delayed because of COVID. So like this is now just getting back up online, but we could detect heavy carbon monoxide like with now technology, basically. And so I'd be really curious, you know, in a hot Jupiter, not like in an Earth-like planet, but we could do HDO in Proxima Centauri B with ELT and a chronograph in one night. So that's pretty exciting. So I never thought that like isotopes would be detected in an exoplanet. If you would have told me that, I was like, you're crazy. But you know, you can't actually do it with high resolution. So I think that's really cool. Maybe we'll get some interesting information on D to H ratios and whatnot. But in order to do that for Earth, like super Earth planets, you're going to need ELT with METIS and adaptive optics, you know, where that's out of the technology future for current instrumentation. But, you know, we could do it there maybe. And then here, if we go back to that, like we're limited on the ground to wavelengths like say less than 5 microns because of thermal background noise. And so we can't look at the big nice IR features of HCN, unfortunately, but there are some around 3 microns, and you can see an atmosphere with HCN and an atmosphere without HCN also has different, you know, spectra. So that would be a potential way to detect that. So, you know, in summary, I'm really excited. We have this technological hurdle that we're overcoming. We're hopefully going to even be able to do smaller, more temperate planets on the 25-year horizon. We're always going to have this interpretation hurdle problem, but that's why, you know, that's why we get paid to look at all these different types of models and how we could start to distinguish some of those. And, you know, I think like Earth took one trajectory on its path. Of course, planets will, you know, it has these molecules, but planets, maybe they make other sorts of molecules. Are those biosignatures? You know, there's going to be lots of weird stuff out there. We're going to try to figure out what it is and see if we can actually detect life. We might see some failed biospheres, but all of this will be really exciting. And hopefully be able to figure out, you know, somewhere in this vast universe of ours, if we have life on another planet. Thank you so much for inviting me.
Thank you so much, Sarah, for the wonderful talk. So I'll now open the floor for questions if there are any.
Hi, great talk, interesting. I was wondering how the phosphine story influenced your work and how you interpret our capacity to detect life on.
Yeah, it's a real interesting question. Because, Clara Sousa Silva first came up with phosphine as a potential biosignature gas. And when she was doing her PhD at UCL in London on the ExoMol survey. And she told me about it. And I was like, oh, that's cool. Phosphine, biosignature. And honestly, if we would have found phosphine in a Earth-like rocky planet around another star, I've been like, wow, we've maybe detected life. And then someone claimed that they found it on Venus. And I was like, no, absolutely not. And that was a real humbling lesson for me, because I realized that, oh, maybe we just don't know, Now, is it even phosphine? That's like one question, right? It's maybe not phosphine. That's like likely, I think. Either way, I think we should send probes. I'm excited about the reinterest in Venus. Venus's atmosphere is weird anyway. If it is phosphine, that's kind of the most exciting potential, though, because then it's like, well, what's creating the phosphine? I don't think it's probably life. Like, there's no real habitable environment on Venus. The water activity level is so low. It's just hard to imagine with the, sulfidic gases and lack of water that you would actually have anything. I mean, if it's life, amazing, also awesome, but probably not. So then, like, what's creating the phosphine? We don't understand something. Or if it's just not phosphine, then it's humbling lesson on like, well, we need to be really careful when we're trying to detect features. If we're like arguing about something in our next door neighborhood, like, how are we going to break these degeneracies for exoplanets? So it just like made me a lot more humble, I think, in terms of being like, wow, seeing my own emotional arc on like, if the Venus controversy hadn't happened, I would have been way more pro this alternative biochemistry option. And now I'm like, I don't know. Will we ever know? Yeah.
So the question that you asked in the beginning of your talk was essentially why aren't we on the work system?
Yeah.
Has there been something that you've learned along the way studying all these different paths that makes you think there's a reason why we're on in this kind of system?
Yeah, I mean, I think I'm really waiting for the James Webb answer on, do star planets have thin atmospheres? I think that's like, I'm not convinced they can, and if they don't, then that like more or less, I think, explains it. However, and if they do have atmospheres, I do think otherwise dwarfs are very habitable environments. So then it's like, are we a 6% event? But yeah, I don't know. Like, I want to wait a few more years before really putting me down on that. Yeah. Great question, though.
Speaking of JWST, do you have are there any plans in the pipeline that are to be observed in any dwarf planets to be observed right now?
Yeah, TRAPPIST. The TRAPPIST system is, I think people have data from like TRAPPIST-1e now.
Yeah.
Nick Callan, I think, is on one of those.
Yeah, there's a couple of students here.
People here. Right? Like, amazing. I want to hear,
Are there anything besides TRAPPIST though? I mean, maybe those who are like within the 20 between 20 and 30 light year range.
Well, TRAPPIST is not that far, but also there are other M-star planets that are being observed. I'm sure people in the room know that list more than me, because again, I'm like a theorist. But yeah, I think LHS 1140b and some other cool systems are also being observed now. So yes, people are going after these systems. Yeah.
If I force you to give a number, what percentage think the chance that you find life before you die?
Oh. Wow. Yeah. I think we'll find molecules that might be biosignatures before I die. And I think we're going to be arguing about whether they are life until I die. Like, I would say almost 100% probability on both. Kind of like the Allen Hills meteorite. People are still writing papers about that, from 1996. They're still going back and forth. No one cares anymore, right? But like, people are still, still arguing about it.
So it's hard from outside the solar system or the
Oh, that's a different question. Also interesting. I think they both have an equal likelihood. Obviously, if we find stuff in our own solar system, that's way more like probably easy to verify and robust detection. So I like, kind of am rooting for that on the more certainty front, but then it's like, well, is it like panspermia from Earth or whatever, for detecting a true second origin, that would be on an exoplanet, unless it's like Titan, that's like not Earth. Enceladus is very like Earth though, it's water, So and Europa, I mean, we really have to look at it. Certainly Mars almost certainly has cross-feeding between Earth and Mars. So
Something like Enceladus, you cannot see anything from distance from there.
yeah, you have to go through the plume, but it's like there, right? It's like the plume that's going into, it's a transient system. Enceladus's water is only stable like 10,000 years, whereas Europa's water has been stable for 4 billion years. So I don't know. It's like, I'm excited about all of it, but I haven't I've only bet money on when we will detect oxygen in a rocky planet, temperate planet, by what year. And I have a bet with Ray Humbert at Oxford for a nice bottle of white Bordeaux.
Well, I might point out that we do see oxygen on planet that crashes on white dwarf stars.
Yes, yeah. But I don't we made very specific and it's just the detection. It's not like any interpretation. It's like the detection of a planet between this radius and this radius and this, So we'll see. Yeah.
When you're observing these planets,
I don't observe.
Yeah. When one is observing these planets, you're seeing the nighttime side of the planet, right?
It depends on what observations you're doing. If you're doing direct detection or transmission, you're getting the light going through the upper layers of the atmosphere of the star. So you're just seeing that upper part of the atmosphere.
But the nighttime side is close. If there was,
but you're not really seeing that. You're only seeing the upper layers of the atmosphere at the terminus part.
yeah. But if there was a civilization.
Yeah, it was like city lights or something.
City lights.
Yeah.
And I guess it's got all neon lights. Would that show up?
No.
Or is it dwarfed by?
Yeah, not for transmission, because again, you're only seeing the atmosphere. But direct detection, there is models on could you see city lights, with direct detection. It has to be really intense. You have say a planet. There's a technosignature paper on this where you have a planet that's, what did they call it? I don't know, it's like a solar farm, or something like that, or the whole planet surface is being, used for some technology, and then you can see that signature. So there's some thoughts on that, but that would be direct detection because you need to see the surface.
Yeah,
And
it's their Christmas.
yeah, they're really into it. They're really
whole
into
bunch of
Yeah.
I like it. The question.
Yeah, let's go for it. Give me $100 billion and I'll make that telescope for you.
Great. I have one final question for you. So you talked about being a little bit pessimistic about being able to detect methane with LUVEX in the future. So what kind of mission concept are you excited about in order to probe
Life, of course, the large interferometer for exoplanets.
Yeah, can you talk a little bit more?
Sure. Yeah. So, I also love LUVOIR, HAVEX, great. I want everything. I want all of the wavelengths. And I do think we'll be able to best break the degeneracies with all of the wavelengths, because there's certain degeneracies in each part of the spectrum that are just very difficult to break. And so by getting a visible optical UV mission, plus I want to know the UV. Once Hubble's gone, we won't know the UV. So I really want LUVOIR. But you just have all the molecules absorbing in the infrared, all the interesting stuff, a lot of the interesting stuff. I shouldn't say all the interesting stuff. A lot of the interesting stuff is happening in the infrared. So you really want those molecules. And then that's this European mission concept called LIFE, the Large Interferometer for Exoplanets. It's kind of a rebooting of, if you have been around long enough to remember Darwin or TPFI. So it's 4 2-meter telescopes, formation flying in space, large Gaussian interferometer, able to do direct detection in the mid-infrared. And so there's a lot of papers written on that, and I'm on the team for that. So that's if I had $10 billion, I would make that mission first, then I would do LUVOIR. But if I had $20 billion, I would do both. Yeah. So I don't know. I need to I don't know. Mine a lot of cryptocurrency or something. Get some more billionaires. I don't know what the fastest way to get that, but I do think we need both.
Great. Well, if that's the end of the questions
then I'd like to thank you again for giving these amazing talks. So another round of applause for